So in this video we want to go over how to graph vertical translations of the cosine and sine functions. And before we dive into it, what we want to recall is from our pre-calculus coursework that if we have any function f of x and we add some real number to it, so some real number, say k, that this translates vertically the graph of f of x, k units up or k units down, depending on the sign of k. So if it's positive, it translates the graph upwards. If it's negative, it translates the graph downwards. And where you would have learned this, for example, would have been in the context of toolbox functions, where let's say you have f of x equals x squared, and then you create some new function g of x equals f of x, which is the squaring function, and then you add something to it, like plus 2. So we really have the function x squared plus 2. And in terms of graphing, what you learned to do was understand where the toolbox function lives. So here's the squaring function x squared. And then what you realized was that adding 2 to the squaring function just translated the graph 2 units upwards. And so this principle of vertical translation or vertical transformation of a toolbox function is going to hold when we're working with trigonometric functions. And so what we want to understand is that for the cosine and sine functions, are the family of all possible cosine and sine functions, that the cosine of x is the toolbox function for all cosine functions, and we want to understand that the sine of x is the toolbox function for all sine functions. So the way that we can deal with graphing function transformation, so here I have a function f of x equals 3 cosine of 2x plus 10. This plus 10 is going to move the graph of 3 cosine of 2x 10 units vertically. So to graph these, kind of the easy thing to do is ignore the vertical transformation and think about what you've learned about graphing functions of the form a cosine bx, because this is something that we dealt with in a previous video. So how do I graph these? So start by establishing a vertical axis. So here's the f of x axis. And then think about, well, what would you do if you were graphing the function and it were not translated 10 units vertically? So let's pretend that this dashed line is the x-axis for a minute. Well, we know that the cosine function starts high, goes to its midline, which is the x-axis, goes below the midline to its lowest point, comes back to its midline, which is the x-axis, and returns to its highest point, and then it continues that pattern over and over again. And it's going to do that unless there's a negative sign on the coefficient reflecting it over the x-axis, which in this case there isn't. So the graph of the cosine function, we know that it starts high, goes to its midline, goes low, comes back to its midline, and goes up high. And in this case, all we need to do is identify that instead of starting on the x-axis, this function's been translated 10 units upward. So the midline, which is usually the x-axis, the midline is usually the x-axis. Now the midline is going to be 10 units higher than the x-axis. Or in other words, the x-axis is the equation y equals 0. So the midline is the equation y equals 0, but we're going to be adding 10 to the midline. So the new midline will be the equation y equals 10. The midline, the x-axis, gets translated 10 units upwards, and we just label a 10 on this. And then the amplitude just means that usually you're 3 units above your midline. Well, if we're translating things upwards 10 units, now we need to be 3 units above our midline. So our amplitude is 3. So we're going to be at 10 plus 3 is 13 units. And we're going to be, the lowest point should be, this distance right here should be 3 units below the midline. So 10 minus 3 is 7. And then we deal with the 2x. We know that a period is usually 2 pi. We know that everything that happens to the cosine function happens in 2 pi radians. So we see that we have an input that has a scalar adjusting it. So we ask the question, when does 2x equal 2 pi? We divide both sides by 2. We see that happens when x equals pi. So we know that the period is pi radians, and we know that the function is chunked into force. So we have high point crossing the midline, low point crossing the midline, high point. So we just take a fourth of the period, which is pi over 4. So we know this first tick mark is a fourth of pi, so we put pi over 4, which means this second tick mark right here is going to correspond to 2 pi over 4. The third tick mark right here is going to correspond to 3 pi over 4, and this last tick mark is 4 pi over 4, which reduces to pi. So we can take and reduce any of these fractions. 2 pi over 4 would reduce to pi over 2. So you can reduce those. I don't think that you need to. So anyways, I think that's the easiest way to graph a vertically transformed function, is just establish the midline and then graph what it would look like if this midline were the x-axis, and then understand that the x-axis, the old midline, has been transformed or translated 10 units in the vertical direction. So we'll do one more example. Here we have -2 sine pi x minus 5. So this minus 5 is going to take the graph of the sine function and translate it 5 units downwards. We also want to notice that the amplitude is 2, and there's a negation on the amplitude, so we're going to get a reflection of the sine function over the x-axis, or in this case we could even say over its midline. So to draw this, I'm going to draw myself my vertical axis. So here's my f of x axis. I know that I'm going to be translated down 5 units, so I'm going to establish a midline that is lower than I ultimately want to draw in my x-axis, and I'm not going to worry about drawing my x-axis yet. And I know this midline is at -5 units. Now look at the function -2 sine pi x and think about how you would graph this. Usually the sine function starts at its midline, the x-axis, and then it goes up high, down low, lowest point, back to its midline. But this negative is going to reflect it. So instead of starting at the midline and going up, it's going to start at the midline and go down. So we're going to draw the sine function reflected across its midline, start at the midline, go down to the lowest point, back to the midline, up to its highest point, and back to the midline, and that gives you one full period of the sine function, and then somewhere up above it is the x-axis. Now we need to identify what's the highest point on the graph going to be, what is the lowest point on the graph going to be, but the amplitude is 2. The amplitude is 2, so we're going to be 2 above the midline, so -5 plus 2 is -3. We need to be 2 above the midline, and we need to be 2 units below the midline at -7. In other words, the amplitude always tells you the distance between the crest and the midline and the distance between the trough and the midline. So that takes care of the basic shape of the function. Now we need to look at the pi x. This pi is changing the period. Usually the period is 2 pi. I'm multiplying by a scalar pi, which is about 3, so the function should be happening about 3 times faster than it usually does. So we want to take a look at the pi x and ask the question, when will pi x equal 2 pi? We divide both sides by pi, we get x equals 2. And our check on work is when I plug in the number right here, For x, will I get 2 pi, which is 1 period? And the answer is yes. So right here, going up to the x-axis, that should correspond to a 2. I know that I'm broken into fourths, so I have my high point, the point where I cross my midline, my low point, and this breaks 1 period into fourths. So I'm going to take a fourth of 2, which is just a half, and that tells me this first tick mark is a half. So 1 over 2, 2 over 2, 3 over 2. This guy right here is 4 over 2, so we can just count up in the numerator and then reduce fractions if we want to. So 2 over 2 is 1, and 4 over 2 is 2, and there we have a nice vertically transformed graph, or vertically downwards.